So in today's last talk, Eva Viehmann will give also the final talk in the series on Shtukas. Please.
Yeah, thank you very much. So final talk in a long day and final talk in this series. So this is the second part on local G-Shtukas, or rather the talk connecting the part on global G-Shtukas and on local G-Shtukas. So let me recall what Tsung did in her talks, or part of it. Maybe first, our goal today is to relate moduli spaces of global and local G-Shtukas. So the setting was the following. We fixed the curve, and in Tsung's talks, this curve was called X, but in my notes it's always C, so I don't try to stick to X. So C is what it was X before. This is a smooth projective and geometrically irreducible curve over F. Oops. Curve over FQ. And then we considered a reductive group. And for simplicity, what we just do is we consider the base change to C of a reductive curve, of a reductive group over FQ. And of course, one can do this with much greater generality. So one could consider a parahoric group scheme over C, but let's stick to this case here. So the ideas and constructions are very similar, but the results hold in greater generality that I don't want to explain in this course here. Okay, and then she had various notions of global G-Shtukas with n legs. There was the variant where you had really n separate modifications, and then she had the one where we get all the intermediate steps and just keep the big one, which is the composite of all of them. I will take the second variant here. So for me, a global G-Shtuka with n legs over scheme S is a tuple well, you have these n legs, S1 to Sn, and then you have a G-torsor and a Frobenius map. So here we have the following things. This curly G is a G-torsor over C cross S. Then these SI are the legs, so the SI are all S-valued points of my curve. They're called legs. And we saw in her talks that there's a difference in the behavior depending on whether these legs are pairwise distinct or not. And as soon as I will do anything with these global G-Shtukas, we will always be in the situation where these legs are distinct. But for the moment, they can be anything. Okay, and then phi identifies, or is an isomorphism between the Frobenius pullback of this torsor over the complement of the graphs of these legs. So we have C of Q with S, and then we take the complement of the union of all the graphs of these SI. Mapping to G and the same restriction here. Okay, and this is an isomorphism. So for her, all of this looked a little bit different because she also considered all these intermediate steps. But if you unravel the definition, then you will see that this is exactly what she had when she forgot the intermediate steps. Okay, so then she had a notation, I think it was Shtukas, and then for G and I is the set 1 to n. I, and then upper I, yeah, this is the moduli stack. Of global G Shtukas. With n legs. Okay, and very soon I will maybe eliminate this I because it shows up twice anyway, and you will see that we will have a lot of decorations up and down very soon, and then we're happy to have one less. Okay, and this had a natural map to the nth power of the curve, just mapping any Shtuka to the collection of legs. Okay, so this is mapping to the legs. Okay, so this is the global situation that we had, and we want to relate to the local situation. So the first thing we do is to construct a global local functor that assigns to any such global G Shtuka an n-tuple of local G Shtukas corresponding to the various legs. And I should say a first caveat that we have here is that we cannot simply start with an object like this. What we have to do is to fix the legs. So all of what I'm presenting today only works very well if we do the following. We fix distinct places. So our next this was the setting. Now comes the global local functor. And the first thing we do is we fix distinct places. Ci in C of FQ bar, and we will only consider global G Shtukas whose legs are in the formal neighborhoods of these particular places here. So in particular, they will be distinct. So yeah, okay, so by C, I denote this tuple C1 to Cn. So this is fixed once and for all. And some notation I denote by A sub this little c, the completion of C to the n in this point C, 1 to Cn of C to the n. Then, okay, so what is this? Well, we've completed an n-fold product of a smooth projective curve in a collection of points. So this is, okay, so let me denote by Fc its residue field. And then this is this residue field Fc, and then formal power series in n variables, zeta 1. Maybe I'm confused. It should be that one, that n. Okay. Okay, and similarly, you can of course do this for each of these points separately. This we also need as notation. So I have ACIs. This is the formal completion of C in the curve C in the point CI, and this is then of course isomorphic to a formal power series ring in one variable for every I. Okay, what else? It's a finite field. Yeah. Excuse me? C is this collection. So here I consider this n-fold product of the curve, and then this is a point of that curve. This is also a point. I mean, it's a point in C to the n. Okay. And of course, I mean, you can do similar things here. I mean, you also have FCIs, right? And this is then for the individual point, and you get a similar description there. Yeah, two more things. You have GCI. This is, well, I mean, the whole group, I assumed the whole group to be just constant and base change of some group over FQ to the curve. And you can also take this base change to spec AI. And well, this is then a reductive group over, well, over a CI. And again, constant, just the base change of the original one that we started with. And one more thing that we need, this is maybe a little bit more or less boring stuff. I consider the restriction of scalars back to FQ of that, of this GCI, and very confusingly, I just emit the C if I pass to that here. Okay, anyway, we wanted a global local functor, so we want to start with a global G Shtuka. And as I said, I want only those that have legs in formal neighborhoods of this given n tuple of points. So I denote, okay, now come my decorations. G, I have, this was what I had before, and then I add an upper C here. Well, this is the fiber product of the original stack of global Shtukas. So this is the formal completion along this point here, essentially. Okay. Okay, so this is this here. This parametrizes global G Shtukas with n legs, and the legs should be all in the formal neighborhoods of these CI here. Okay, and now I take an element in there, an s-valued point. So let G underline. So this is such a tuple of SIs that are now in the formal neighborhoods of the CI, G, and phi. Be an s-valued point of this formal completion. Okay, I need one more notation. Maybe I can put this there. SI is the product of S over FQ with F CI. And then, well, I want to produce for every I from this global G Shtuka a local G, or from this global G torsa at first, a local torsa. And so I just base change. It's nothing but that. So I take the base change of G to SPF AI times FQ hat S. Okay, so what is this? This is SI of Z, right? I mean, this SPF AI, this is formal power series in one variable over FCI. And so we get this here. So we base change to here, and this defines a GCI torso. Well, on this here, on SIZ. This is almost what we want, but recall yesterday what we did for local G Shtukas was not that we had G torses on this somehow formally extended base, but rather we had L plus G torses on Si. So this is the only step one has to do, and it works out. So what we have here is we have an element of the torses, so of H1 of FQ GCI of, sometimes I write SI and sometimes of SI. I think this is at least consistent like this. And then we have to use a natural bijection or even equivalence of categories between this set here, or the category of these torses. We have a natural equivalence of categories to what I said, the L plus G CI torses on SI. Okay, so this is a proposition that there exists such a natural, or this is naturally an equivalence of categories. Okay, so at this step one has to show a little bit, but it's not too difficult. Okay, and in this way, what we get is for every global G Shtuka and every I, we get here an L plus G CI torse on SI. So this is the first ingredient that we need for local G Shtuka. And then, yeah. G is a torse, right? I mean, G is a torse on C times S. I mean, it's a point in the Shtuka space, but a point in the Shtuka space consists of the legs, the torso over G times S, C times S. And so here I don't have an underline. I just consider the torso at first, and I base change that. Yeah, right. Yeah. Other questions? Yeah, it's a category of torsos. Yeah, maybe I should say just as an equivalence, a bijection. I mean, I don't need equivalence of categories here. What? I need just a map, in fact, right? You saying it's not an equivalence, or? Yeah. Ah, okay. Okay, then ignore my erasing this. Okay. Anyway. Okay, so. Okay, so now somehow we're done for the torso part, and then I don't want to say much about the Frobenius. I mean, you just go through this construction, and then you see that the global Frobenius phi induces on these local torsos also Frobenius isomorphisms. Why this is true? I mean, you have to, I mean, if you have such a torso, you would take the corresponding descent datum, and then you have to work a little. I mean, for one direction, I think you have to reduce mod powers of Z approximated by finite things, and then you use FPQC descent and give some short argument. But I don't think that there's really a deep idea in there. I mean, you just have to look carefully at what you have and then work this out. Yeah. Okay. Right. I mean, somehow what you do is, you move somehow the Z from here to there, right? I mean, yeah. Right. Yeah, this is correct. Okay, and then I just say without any further ado that this phi induces Frobenius morphisms, say phi I on the this element in there, that this I call GI maybe, GI, and then tracing through this construction, you get also that the Frobenius morphism induces Frobenius morphisms in this local setting. So altogether, this may be the first very basic relation between global and local, is that we get a global local functor maybe I call it L for local, and you consider these this construction here for every leg separately. This gives you a functor from okay, which decorations do I have? G and then I, and I took the formal completion at C to the product of all I of the moduli spaces of local Shtukas. Okay. I should say this construction doesn't really depend on the fact that we complete in points that are legs. We could do the similar construction starting with a global G Shtuka. We can complete in any point of the curve. If it's not a leg, then it's less interesting maybe because nothing happens there. It's, the Frobenius is an isomorphism. We get an étale local Shtuka in that way, but one can do that. So same construction. It's also possible for points, say X, which are in C, but not one of these. And if you do this in any other point, then you get an étale local Shtuka, local G Shtuka, GX Shtuka. Maybe move that. And well, this is sometimes useful if you want to define level structure for étale. And if you have étale local G Shtukas, then this is very helpful. Away from these critical or from the legs, you can easily define using this. You can define level structure. But also in general, I mean, we can use this global local functor now to define in a rather ad hoc way level structures and also bounds. Recall last time we had these bounds on the denominators. We can define bounds in the global situation using the global local functor. So an ad hoc definition of level structure and bounds. Whoops, that was maybe a bit too much. Okay, so for level structures, okay, so for say D0 in C, a finite reduced subscheme, in other words, finitely many points of C. And we consider such finitely many points where we want to define the level structure. And then we consider a global Shtuka such that the legs and the complement of the set D0 for I. Okay, so these are the places where we want to define the level structure. So for every place, we have to fix some subgroup somehow determining which level structure we want. So we fix a subgroup UV in L plus G V of FQ open and compact. And denote by U the product of these UV. And then, well, the integral level structure or the U level structure on G is defined to be, well, I simply consider the corresponding associated local G Shtukas at all these places, and I define the UV structures that I defined last time in my last talk at the end on each of these local pieces. Okay, so a UV level structure on LV. I write LV. I mean, I didn't introduce that. I introduced only L1 to Ln, but by the same construction. Maybe I can put that notation on this upper board. So this étal local G Shtuka here, this I will refer to as Lx of G underline. Okay, so we consider this LV of G underline, and then I consider level structures in the sense of yesterday's talk on these, and this will be what I mean by a U level structure on the global Shtuka. And okay, there's one can define a stack of global G Shtukas with U level structure. So we get a stack Shtukas, global G Shtukas with legs corresponding to, I wanted to leave this out, corresponding to I, and then I put the level structure here. So this is this U, and I still consider the formal completion in C. So you see, that's why I wanted to have as little decoration as possible. And we can consider bounds, and we want to consider bounds. So, and also for the bounds, I want to do it in this ad hoc way using the local structure. This is not what one usually does in the global, when one defines moduli spaces of global Shtukas. So for these moduli spaces of global G Shtukas, I think Warshawski has some global definition. But there it's not completely clear why this is the same as what I'm doing. So okay, so my global G Shtuka G, no, I will have to fix mu1 to mu n, a tuple of an n tuple of bounds. So these are elements in X lower star of T dominant. And I denote by mu this tuple. Right, so these are the n different bounds that we need for the n different places. And now such a global G Shtuka having legs and the SIs, and then a torso and a Frobenius. This is bounded by mu. By definition, if, well, for all I, the corresponding local G Shtuka Li of G underline is bounded by mu I. In yesterday's sense. Okay, and yeah, in this way, we get again a substack Shtukas, G Shtukas, modifications corresponding to I level structure for U, completion in C, and less or equal to mu. Okay, so this is all the conditions that we want to impose. Okay, and as I said, I mean, it's slightly different, the bounds, than what one usually does, but this is the one that works well if one wants to compare local and global. Okay. Yeah, now we want to essentially generalize all the local-global compatibility results that you have in the arithmetic situation. So there are three kinds that I'm heading for. The first is generalization of Serre-Tate to this context here. The second is the Rappaport-Zink uniformization morphism, and the second is the foliation structure on Newton strata. So for those who are familiar with the arithmetic situation, all of these comparisons have an analog in the situation here. Yeah, that's right. Yeah, the difference is not big. That's right. Yeah. Maybe the thing one might worry more about is that we have to fix the places and cannot let them vary. But okay, I think that is something one has to do anyway. Okay, so first of these, Serre-Tate theorem. So classically, the Serre-Tate theorem gives an equivalence of categories between deformations of abelian varieties and deformations of the associated p-divisible group. Okay, and so if you want to have a translation, this means we want equivalence between deformations of a global G Shtuka and deformation of the corresponding associated local G Shtukas at all the places. So setting as usual, I fix my places C1 to Cn and C. S is one of these nilpotent AC, and then I wanted deformations to S. So I consider a closed subscheme. So say J is the inclusion of a closed subscheme. So this is a closed subscheme defined by a locally nilpotent sheaf of ideals. Okay, and then I start with a global Shtuka, a global G Shtuka on the smaller scheme, and I want to deform to S. So G underline. This is G, SI, G, and phi. This is in the G Shtukas for I, and I need to complete that C, but I don't want to talk about level structures at the moment. You could, but okay. Over S bar. And then deformations to S of this G underline, of this fixed global G Shtuka G underline. Well, this is the category of pairs, say G underline tilde and alpha, where G underline tilde. Well, this is in Shtukas G I C of S. And then you want that alpha is an isomorphism between the reduction to S bar of this G tilde and the original global Shtukas. So this is from G underline to G, tilde underline, and then base change to S bar, an isomorphism. And similarly, of course, you can do this for local Shtukas, right? I don't even write down what the definition is. Yeah, just the same. So similarly, you have deformations to S of L of G underline. Here I do all the local Shtukas at once. So this is a product. Now it's getting a bit tight here. So it's a product over all the places of the corresponding deformations of the Li of G underline. Okay, and yeah, you can figure out yourself what this is, how this is defined. Okay, and then excuse me? I didn't quite understand. Maybe we can discuss this afterwards. No. Okay, and then the theorem is as follows. Okay, yeah, I didn't put any names on any of these. So this most of what I'm doing today is in the thesis of Stefan Neupert, but this Tate theorem is also, well, you can find it in Neupert's thesis, but also in work of Arasterat and Hartel. But as I said, for all references, look at my ICM notes, and there I explain this. Okay, so let S, okay, I didn't say what S is over there, but it's slightly more general. I consider any Deligne-Mumford stack S. Over the formal spectrum of E power series in Z1 to zeta n, and such that all these zeta I are locally nilpotent on S. That's that. Or even this ideal here, yeah, this ideal here is locally nilpotent on S. And then I consider wait, what am I doing? This is not really what I want. I'm sorry. I don't think that I have to assume this. I mean, we introduced the setting over there. Let's just stick to that setting. So sorry. Let's just write the global local functor induces an equivalence of categories. I mean, I introduced everything on the other board, so it just induces an equivalence of categories between these two deformation categories. Def of to S of G, and then you have this global local functor here, def to S of L of G. Okay, and yeah, this is the product of over I def S of the Li of G. So here, yeah, you have really all the deformations. And of course, it looks a little bit different from the arithmetic situation because you have these n legs here. But okay, other than that, it's really just what you expect. Okay, but I don't want to say much about this somehow very first comparison, but I rather want to spend the rest of the time to also explain what this Rappaport-Zink uniformization means here, uniformization and hopefully also foliation structure. Okay. Okay, so what does uniformization mean? We want to compare moduli spaces of, I mean, this is still for somehow individual local and global Shtukas. Now we want to compare the moduli spaces. And okay, so we need some more notation. We fix a maximal torus T and B, a Borel of G. And Ci's and mui's as over there. And then for every I, we fix a local G Shtuka, say GI underline, and I assume that it's trivialized. So local GI Shtuka over E, and E is the field of definition of mu. And I trivialize this local G Shtuka so that it becomes the trivial GI torso. And the Frobenius can then be written as given by an element Bi in LGI of E times Frobenius. And yeah, for completeness, I have to say this, I assume this to be decent, but I don't want to comment on this, a decent local GCI Shtuka over spec E. Okay, and once we have fixed this, we have an associated Rappaport-Zink moduli space of local GCI Shtukas corresponding to this GI underline and the corresponding mu I, this bound that we fixed. I mean LGI. So this, yeah. I mean, already for the local, the global local functor, you ended up in GI because I think I erased it already, right? You had this construction where you ended up in SCI, which was the base change of S. And if you want to go back to S itself, then you need to have this Weyl restriction. This is why this comes in. Yeah, it's a bit tedious that you change the group here, but that's what comes out. Okay. Okay, so for every I we fix this. So we get Rappaport-Zink moduli space. M breve, how do I call this? M breve Bi less or equal to mu I of local GCI, no, GI Shtukas corresponding to, well, this GI underline and the bound mu I. So this is the kind of moduli space that I constructed last time. Okay, and then the uniformization theorem. Again, I should put the names Neupert and Arastirat and Hartl next to it. Okay, and now I want to formulate this really in this greater generality. Now it's more interesting. So I consider a Deligne-Mumford stack as, as I said, now I want this general situation that we had before. So it's over the spectrum of E, and I want of all these zeta I, and I want that all the zeta I are locally nilpotent, such that zeta 1 to zeta n is locally nilpotent on S. Then, well, I want a uniformization morphism, and this will be a map from the product of these Rappaport-Zink moduli spaces to the moduli space of global G Shtukas. Okay, and the idea is that we have somehow a fixed base point in the moduli space of global G Shtukas, and then this morphism is constructed by doing the following. These Rappaport-Zink moduli spaces, they consist of pairs, a local Shtuka, plus a quasi-isogeny to the fixed one, to this fixed GI underline. And we use these quasi-isogenies to modify the global G Shtuka that we have in our fixed base point to somehow construct the whole morphism. And so the first thing we have to do is to fix such a base point. Say G0 underline. This is now in this G upper I, and then I have maybe level structure and a completion in C of S. And I should also say less or equal to mu. Did I put this up or down? Well, doesn't matter. I want the bounds by mu. And U is a congruent subgroup, or this is level structure, away from the places, from the legs. And we want the space point in such a way that we can later apply the local quasi-isogenies. So for each CI, assume that there is an isomorphism between the local Shtuka, say L CI of G0 underline, and my fixed local G Shtuka GI base change to S, and fix 1. Okay, so we make here really a lot of choices. We choose G0, and we choose for every I such an isomorphism. And we assume that we have chosen this G0 in the correct way so that there are such isomorphisms. Okay, and then okay, then we have a morphism of formal stacks over this SPF E and then all the zeta I. From, well, the product of all Rappaport-Zink spaces, so of all local moduli spaces, times SR over SPF E all the zeta I to S to our moduli space of global Shtukas with all the decorations that you want. I had here U and less or equal to mu and C. Okay, and which is improper and formally tau. And okay, so last time I didn't say much about Hacker action on the moduli spaces, and I don't know if I don't recall how much Tsung said, but once one has these group actions on the moduli spaces, these Hacker actions, then this uniformization morphism is also compatible with the Hacker actions. Right. Okay, so I have 10 minutes. Let me see. Okay, so what is the image? I mean, you could ask, I mean, on the left, we've fixed a lot more data than on the right, right? So we have this uniformization morphism for every choice of BIs, for example. As long as we find some such global Shtuka G0 satisfying that the property that we have such isomorphisms. So what's the image of this map here? So each geometric point, so remark, geometric point of the left-hand side is mapped to the following thing. Well, something that I would denote by N G underline and then upper BI. And this is the so-called Newton stratum for this particular data. So what is this? Well, this is the locus in this Shtuka space with all the decorations, where the associated local G Shtukas are isogenous to the given local G Shtukas, and recall these were defined using these BI. So this is why I put BI and not GI underline. The idea is that this map was constructed by taking the base point and then modifying at these n places using the quasi-isogenies that are given from the Rappaport-Zingst space. And so in a natural way, you see that what you get locally is, well, it's quasi-isogenous to what you started with. And so you end up being in this Newton stratum. And these Newton strata, they correspond, as you see, to the isogeny classes or quasi-isogeny classes of these local GI Shtukas, and there are only finitely many of them. So for every I, we have finitely many choices for these GI underline, so that indeed we find such a base point G0. So so the Newton stratum this corresponds to the quasi-isogeny class of well, of this n tuple of local GI Shtukas GI. And recall they were trivialized And the Frobenius was given by an element Bi. And quasi-isogeny means on these Bis that you can Frobenius conjugate Bi. So this means if you modify this or replace this by a quasi-isogenous datum, this means that you replace this Bi by a sigma conjugate. So this only depends on the sigma conjugacy classes of the Bi. And by sigma conjugacy class, I mean the following, say Bi in parentheses. This is the set of all G inverse times Bi times Frobenius of G, where G is now anything in L Gi of FQ bar. And well, if you have this additional condition that you want to find G0, a global G Shtukas bounded by mu, such that locally it's isomorphic to this Gi underline, then this is contained in a finite set denoted BCI and μi. I don't have the time to explain this, but this is a finite set. Right, and now in order to continue and refine this uniformization morphism, you choose within each of these sigma conjugacy classes or isogeny classes a particular representative. So you don't start with any GI underline, but you choose one within the given quasi-isogeny class that is of a particular nice kind. This Bi has a representative say Bi, maybe I call it Bi0 in the normalizer of T, so in N of Fp bar of Z, so this is the normalizer of T, such that if you map this to the extended affine Weyl group, which is the normalizer of blah, 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 modulo T of, so this is normalizer modulo T of Fp bar power series Z. This is the extended affine Weyl group. If you map it here, then this should be an element of so-called fundamental alcove, such that the image, let's say, has shortest possible length. And one can also explicitly say what this length then is in terms of the Frobenius conjugacy class. And well, if you know the arithmetic picture, what I'm doing here at the moment is I replace a random p-divisible group by a so-called minimal p-divisible group in the sense of ORT. So this is somehow the function field analog or group theoretic analog of minimal p-divisible groups. And now, instead of starting with this GI underline corresponding to any Bi in the class, you can always take this one and get the same morphism there. Okay, and now I have very little time. Maybe I just very briefly say what this foliation structure is now doing. Okay, so we consider inside the Newton stratum an even smaller piece So we have the Newton stratum, say, for these BI, which is part of the global Shtukas moduli space, C and U and less or equal to mu. This was the Newton stratum, and recall here we fixed the isogeny classes or quasi-isogeny classes of the local G Shtukas associated with the global one. And now I want to consider in here an even smaller piece. Maybe I denote this C and then VI0. This is the locus where the Li of G are isomorphic to the local GI Shtukas given by these particular representatives of my sigma conjugacy class. Okay, so this is, I fix really the isomorphism classes at all these points. This is still a non-trivial thing. The global G Shtuka isn't determined by this. Okay, and this is represented by a formal scheme over the formal spectrum of AC, and this is called a central leaf. Okay, since I'm a bit over time already, let me just say, okay, so the next steps are then one defines Igusa varieties in this context. As covering spaces of these central leaves. Yeah. Of these C VI0 by trivializing or by adding trivializations of the GI Shtukas. So by adding trivializations of the GCI local GCI Shtukas. So the idea is we know over the central leaf that there is an isomorphism to this fixed one, and now you really fix consider pairs of local G Shtuka plus an isomorphism to this one, and in this way you define Igusa varieties, and then okay, maybe at least I write down the final theorem. So you see the uniformization morphism on the left is, of course, very far from being surjective. It ends up being in the Newton stratum, but even it doesn't hit the whole Newton stratum. It's really, unless we somehow have the unique closed Newton stratum, this will the image will be way too small. And so the improvement is the following. There's a natural formally Ital morphism of formal schemes over I have to say in here somehow one small thing is that we also have always to pass to the perfection of everything. Otherwise, I mean, in the yeah. So this is probably only a technical thing, but at the moment one has to require this. Okay, so we take the product of all these Rappaport zinc moduli spaces, their perfection, that's all equal to mu I, and perfection and product over all I. And then we take the product with the corresponding Igusa varieties and their perfection over SPF AC perfection. And this then maps to the Newton stratum. Perfection. And yeah, so this is the formal completion of the global moduli space along the Newton stratum. So this is the formal completion of this global moduli space, blah, 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 blah. So all these decorations along the corresponding Newton stratum. Okay, and this is then this foliation structure that I was talking about. So yeah, okay, maybe I stop here. Thank you.